All right, in this video, we're going to introduce the idea of integration. So integration is going to be the opposite of finding the derivative. So up to this point, we have worked with the function. We derived it to get f prime of x, and then sometimes we took the derivative of that to get the second derivative. So when we work down this way, we find the derivative. Okay, now we're going to do the other half of the course. So we're going to be able to work our way up. So if I give you the derivative, we can do the antiderivative to find f of x, which is what we're going to call integration. Okay, and the symbol for that is going to be that. Okay, so if I'm here, we could work our way up to this by integrating up. Okay, so let's say you're given a function, so y equals x squared. If I was to derive it, we get dy dx equals 2x. So what we're going to try to do is come up with what the function was before it was derived. That's the idea, okay? So you could bring this up here like that. So I could say dy equals 2x dx. So just like division undoes multiplication, addition, subtraction, integration is going to undo finding the derivative, and vice versa when we get to it later. But for right now, we're going to say that integration undoes deriving. So if I want, this is a derivative, this is a derivative. So if I were to integrate both sides, I would just get the function. That's what it was before it was derived. Now it's the complete opposite. So before we would multiply and subtract, now we're going to divide and add. So I'm going to add the exponent by 1, divide by the new power, okay? So we'll practice that, but it's going to be, so it's 2x to the first power. I'm going to add 1 to it to get 2, divide by the new power, and we get y equals x squared. So there you go. So I ended up back with what I started with. Now there's one thing we need to consider when we integrate, and that's called a constant of integration. So anytime I integrate, I need to add a plus c. And the reason is, my original function, let's say I had, well, we did have what, x squared. But let's say I had y equals x squared plus 2. Or y equals x squared plus 100. If I derive all of these, we get 2x, we get 2x, and we get 2x, because this constant goes to 0. So there's no way of knowing if there was a constant, and if there was, what was it? Okay, so to account for that, we put a constant of integration plus c. All right, so again, it's called the antiderivative. A notation you'll see with this big F is going to, and this doesn't have to be like this. Okay, the AP is very creative in how they do things. It doesn't mean it has to be this way, but a lot of times you'll see you integrate little f of x, which is the derivative of big F. So when you integrate, you get big F of x plus c. Okay, so this is the derivative. This is the actual function. Okay, all right, so let's look at this one. So we start with x squared. We're going to raise it up by 1. So x cubed, divide by the new power, and add in your constant of integration. All right, so for something like number 1, is you don't ever have to do this. I'm going to do it once. Don't have to do it again, but know that you can break up the integrals, okay? So I could write this as x squared dx plus the integral of 7 dx. So we go up by 1, divide by the new power. So 7, so a constant is a variable, but to the 0 power, right? Because x to the 0 is 1. So I'm going to raise it up by 1 to get 1. So plus 7x and then plus c. So here we've got 4x cubed over 3, 3x squared over 2 minus 9x plus c. So one thing to make note of, there's no product rule, there's no quotient rule for integration. So we are quite limited in what we can integrate. So a lot of times it's just going to be to rewrite what's inside the integral, so we are able to integrate it. Okay, so square root of x is just x to the 1/2 power. All right, so we're going to raise it up by 1 to get 3/2. So we're going to get x to the 3/2 divide by 3/2, 5x, raise it up by 1 to get 5/2, divide by 5/2, and then plus c. So I'm just going to flip it to get 2/3, x to the 3/2 power. So 2/5 times 5 is 2. So 2x to the 5/2 power plus c. This is x to the 3/4. So we're going to get, so x, so add 1, you get 7/4. Divide by 7/4, which is 4/7 out in front. 1x to the 0 power becomes x to the 1st power plus c. For number 5, I'm going to rewrite this as the integral of -3x to the -7 dx. I'm a huge fan of taking out constants. Try to get in the habit of doing that. So this really is -3, the integral x to the -7 dx. So it's -3. Raise it up by 1, you get to the -6 power over -6 plus c. So we're going to get, so this becomes a 1 and a 2. So it's going to be 1 over 2x to the 6th power plus c. So for this one, I'm going to want to rewrite it. So we've got the integral of 1, because I'm going to do x to the 4th over x to the 4th, and then minus 3x to the -2, and then plus 5x to the -4. And then we just integrate term by term. So we're going to get x, and then we're going to get -3x, so it's the -1 divided by -1. So we get -3x to the -1 over -1 plus 5x to the -3 over -3 plus c. So I'm going up by 1, divide by the new power. So we're going to get x plus, so 3 over x, and then minus 5 over 3x cubed plus c. All right, so for something like this, you're going to want to expand it out, because really, for what we do, you're going to want to integrate term by term. So when I FOIL this out, you're going to get 16x to the 4th power plus 24x squared plus 9 dx. So when we integrate, we're going to get 16x to the 5th over 5 plus 24x cubed over 3 plus 9x plus c. I'm going to leave it. You could change the 24 over 3 to 8, but it's fine. All right, for number 8, we've got x to the 4. We're dividing by 4, so this becomes a 12. This is x cubed, go up by 1, divide by 3, so I'm going to get 6 on the bottom. X squared over 2 minus 3x plus c. All right, so here are our trig functions. So we're just going to keep adding. Okay, you have the 6 derivatives. Now we have the 6 integrals. So let's look at this. So integrate sign is actually negative cosine. So you could check by finding the derivative. So derivative of cosine is negative sine. We never, you'll notice here, is there's no negatives on the integral side, it's on this side. So even though the derivative of cosine is negative sine, you have to put the negative here. So integrate sine, you get negative cosine. And so derivative of sine is cosine. So that's why this one is positive. Okay? And then, so you'll notice all the cos in the answer have the negatives. Okay? And these are very specific. Okay, you'll notice here there's sine and cosine. There's no tangent, there's no cotangent, there's no secant, there's no cosecant. Okay, these are very specific to the derivatives. Okay, integration can be very difficult. For what we do, it really has to follow, I don't want to say a chart, but it's going to either be term by term, or it has to fit exactly these, okay, or we cannot integrate it. All right, so for number 9, again, just term by term. So we're going to get x cubed over 3. All right, so we've got x cubed over 3, and integrate secant squared, you're going to get tangent. So plus tangent of x plus c. So here, is you have to be able to get it to one of the ones above. So I'm just going to manipulate it a little bit. So we're going to get secant tan, so secant x, tan of x, minus secant squared of x. So secant tan is secant, so secant of x. And then secant squared is tangent, so minus tan of x plus c. All right, so again, is you have to be able to manipulate it using trig, okay? So cotangent is cosine of x over sine of x times sine of x. Cancel, cancel. So I'm integrating cosine. Integral of cosine is sine. So integral of cosine of x equals sine of x plus c. Same thing here, separate it. So I'm going to do sine of x over cosine of x times 1 over cosine x dx. So sine over cosine is tangent. So integral of tan of x. 1 over cosine is secant. So secant x tan x is secant of x. All right, here we've got secant squared of x. So this is going to be tan of x. Sine is negative cosine, so negative cosine of x. And then cosecant square is negative cotangent, so plus cotan of x plus c. All right, and then here we've got, I'm going to take out the negative. It looks funny, so like that. So secant x tan of x minus cosine of x. So secant x tan of x is secant of x. So it's going to be minus, so secant of x, and then cosine is sine. So minus sine of x plus c. So we get negative secant of x plus sine of x plus c. All right, so now we're going to add some more to this. So we've done deriving e to the x. When we derive e to the x, you get e to the x. So when we integrate e to the x, you get e to the x. All right, so pretty easy. It's the easiest one, okay? When we derived an exponential with a different base, so d dx of, let's say, 2 to the x, we rewrote it. We multiplied by ln of 2, and then we times it by the 1. Okay, so the same thing, it's just a little reverse. Okay, so we still rewrite it, but you divide by, and then integral of 1 over x is ln of x, because we know that the derivative of ln of x is 1 over x. Okay, all right, so again, I'm an advocate. I know it's not necessary here, but it will get a little bit more challenging, so I do encourage you to take out the constants on the top. So 2, even on the bottom, if you had like a 2, you could take it out as a half. So this becomes 1 over x dx. 1 over x is ln, so it's 2 ln of x plus c. This one, integrate 1 over x, which is ln of x, so we get ln of x, and then minus sine of x would become plus cosine of x plus c. All right, here, so this is exponential, so you rewrite it. You divide by ln of the base. You're also dividing by the derivative of the exponent, but the exponent's always going to be 1, okay? And then cosecant squared is negative cotangent, so negative cotan of x, and then plus 2x plus c. So this one, I would rewrite it as 3 the integral of e to the x dx. When we integrate e to the x, we just get e to the x. So 3 e to the x plus c. All right, so let's run through what is a differential equation. So we're going to spend a whole chapter on it. This is chapter 5, but they like to introduce it early on. It's very, very simple, okay? So a differential equation is going to be an equation with the derivative in it. So for example, you know, yeah, something like this, dy dx, d squared y dx squared, dy dx. Okay, so it's going to have a derivative, okay? Now, to go from the derivative back to the function, we integrate, okay? So everything that we do in this class is going to be a separable differential equation. So for example, let's say you had dy dx equals x squared. So that's the derivative. So I want to work back to what it was before it was derived. Because when it was derived, I got x squared. And the way that we do that is we integrate. Okay, so the first thing we do, and we call it separation of variables, is we separate variables. Meaning the dx needs to be with the dx, the y needs to be with the dy. Or, yeah, the y's need to be with the dy and the x with the dx. So I'm just going to bring this up like this. Once I get the variables separate, I can integrate both sides. I'd integrate, so you get y equals, and then it's x cubed over 3 plus c. And that's really it. So we've been doing it, okay? There's a lot more to it, but again, this is the original function. So this is what we call a general solution. And see if you can follow here, but we have, let's say I have the graph y equals 1/3 x cubed plus c. So this is an x cubed graph. I'm going to graph it here. That is going up 1/3 as fast, so it's not quite as quick as normal. So it's, let's say it starts at 0. Well, we don't know that for sure. Let's say it starts at 0 and it kind of just goes up like that and then down like that. But it's plus c. So I don't really know what the c is. It could be y equals 1/3 x cubed plus 1. All that would do is would be shifted up here, but it's the same exact curve, like that. It could be plus 2. So then it would be here. And so forth and so on. Okay, it could be plus 1, 2, 3, so plus 3, like that, like that. So when it's written like this, we call this a general solution. So it sort of represents a whole family of functions. So this would be a family of functions. But if I told you to solve the differential equation that runs through the point, let's say 0, 1, well, then it becomes very specific. Then I am specifically talking about this graph here. And I would want you to find the solution to that graph. And we could simply do that by just plugging in and solving for c. So for example, I could, let's use this equation here. I could say 1 equals 1/3 0 plus c. So c equals 1. I'd say y equals 1/3 x cubed plus 1. So it's the one I highlighted. So that's one of many functions, okay? So when we have the plus c, it's what we call a general solution. It represents basically the whole gamut of them. I mean, it could be shifted down here, like that, and so forth and so on. But until I give you a specific point, then it becomes a specific solution. So that's all that this talks about. All right, so it's to solve the differential equation. So again, the first step is going to be, this is so great to get on the AP exam, easy 9 points, okay? So you separate variables. So separate. You integrate both sides. And don't forget your plus c, okay? All right, so I want dy equals 5 dx. We're gonna integrate. Integrate. When you integrate dy, you get y. So you get 5x plus c. Here I've got dy equals, so 2x to the negative 3 dx. We integrate. We integrate. So you're going to get y equals, so it's 2x. Raise it up by 1. So if I raise it up by 1, it's going to go to negative 2. And then divide by the new exponent like that. So we're going to get y equals, so it's negative 1 over x squared plus c. All right, so this is find the particular solution. Okay, so now we want to find a specific curve that runs through the point 3, 3. So the first thing you want to do, the notation here is a little funny, but it is a differential equation because it's a derivative. So we're going to write it as dy dx. So dy dx is equal to negative 12x cubed. Separate. So dy equals negative 12x cubed dx. Integrate. Integrate. So you get y equals, so it's negative 12. Raise it up by 1. Divide by the new power plus c. So this is my original function. So y equals negative 3x to the 4th plus c. They want it to run through the point 3, 3. So this is going to come out as a 3. This is 3 to the 4th. So we're going to get negative 243. So 3 equals negative 243 plus c. So c is equal to 246. And then I just rewrite it here. So we're just getting a habit. We're going to do much more complicated ones. But you always want to plug back into where you substituted in. Okay, so we've got y equals negative 3x to the 4th and then plus c, so plus 246. All right, here we've got dy dx. Actually, this is dy dt, so let me rewrite this. So dy dt equals e to the t. So dy equals e to the t dt. Yes, you must pay attention to it. They very often use t instead of x, okay? All right, so we integrate both sides. Integrate, so we're gonna get y equals, so e to the t plus c. We have the point 0, negative 6. So it's negative 6 equals e to the 0 plus c. That goes to 1, so we get negative 7. So then y equals e to the t minus 7. All right, so for this one, is understand that if you have the function, the derivative, the second derivative. Okay, when we worked our way down, we would derive it and we would derive it. We can do the same with integration. It's a smidget more challenging because we have to consider that constant of integration each time you work your way up. Okay, so we would integrate, but we got a plus c. We would integrate, we have a plus c. Okay, so just something to think about. All right, so I'm going to integrate. I don't know the perfect notation for this, but we know that the second derivative equals 2. So when I integrate it, I'm going to get the first derivative. So we're going to integrate, but you want to put the dx over here. And then we're going to integrate. So when we integrate, we get the first derivative. So it's going to become dy and then equals 2x plus c. I'm not going to lie, because I don't know what the perfect notation here is for this. All I know is that I'm integrating the second derivative to get the first derivative. So this is the first derivative. Now we know that the first derivative at 2 is 5. So 5 equals 2 times 2 plus c, so c is 1. So I know that the function for f prime now is going to be 2x plus 1. So this is dy dx. So now I can bring up the dx like that, separate, integrate, integrate. Like that, okay? And then just to finish this off, because we want our function without a c value, so we know f of 2 is 10. So this is 10. This becomes 4 plus 2 plus c. c is equal to 4. I'm going to plug back into here. So we're going to get y equals, so x squared plus x plus 4.